estúpido.
This woman is mentally ill. She is being treated with psychoactive drugs that will affect her behavior.
What is God saying to you now, Sally?
This is me when I came to the hospital. I was very upset from many worries. They make me sick. I could not even talk to the doctor. This is me 4 days later, after the doctor gave me some medicine to help me. Now I'm not so mixed up. I talk to him okay. This is me when I'm ready to leave the hospital. I am better now.
I'm John Darley. 1 out of every 10 Americans requires treatment for mental illness. And drugs, as you have just seen, can show dramatic results, for they produce profound effects on human behavior. During the last 10 years, they have revolutionized the care of the mentally ill. But just how do these psychoactive drugs work? This is the key question in the field of psychopharmacology. Many scientists are searching for the full answer. The major contribution of the psychologist in this search is his specialized ability to observe and to measure behavior. Engaged in research of this kind is the chairman of the psychology department at the University of Indiana, Dr. Roger Russell.
The first thing we can say about psychoactive drugs is that they affect behavior. Now, this may seem very obvious to you, but it is of tremendous importance not only that drugs affect behavior, but that specific drugs affect behavior in specific ways. The psychologist has developed methods and techniques for observing and measuring behavior. These procedures have double value. First, they may be used to obtain knowledge which is essential to the general medical use of drugs, including undesirable side effects. And second, they may be used for research at the basic level. Now, all aspects of behavior, from complex problem solving to general level of activity, are important to us. We do a great deal of our testing with animals. The research designs are complex, and they take some time and care to interpret the results. Let me give you some simple demonstrations of the sort of thing we do. Now, this is a test of complex problem solving. This rat has learned that there's food at the other side of this closed field. The barriers in the field may be rearranged to form different problems. The rat has not seen this particular problem before, so if we put him in the starting box and release him, we'll be able to measure the time it takes for him to go from the start box to the food. Well, that animal took 14 seconds to run the maze. That's a very good time for the first trial on any animal. I'm going to take him out, put him in this cage, while we see how well this second animal can do. This is a comparable animal in terms of his past performance. This animal has been drugged. It's also the first time he's seen this particular problem. Let's see how he compares with the animal you've just seen. I'll treat him in exactly the same way. Now, you see, it took him 32 seconds to solve the problem for this first trial, and you also may have noticed that his coordination was definitely not as good as his partner's. Now, this is a kind of complex behavior made up of many simple components. We're as interested in the simple components as we are in the complex behavior itself. This equipment is designed to study what we call a simple escape response. When I put this normal rat in the water, he swims as rapidly as he can to the escape platform at the other end. And here is how a drugged rat, again with the same drug, responds to the same situation. Many different species of animals are used in studying the effects of drugs upon behavior. In terms of the practical uses of drugs, monkeys have advantages as experimental subjects in being more similar to man than rats, for example. But no animal's reactions are identical with man's. Therefore, it is always essential that research be conducted with human volunteers. Early clinical tests with a small number of patients are done under careful medical supervision. If the drug seems to be effective, then tests on a larger scale, conducted by teams of physicians and psychologists, are begun. It is only after these many tests have been successfully completed that the drug may be released for public use. As we know, psychoactive drugs may do great good. The treatment of the mentally ill has improved enormously since their development. But these drugs do not in themselves effect a cure. They may help to create conditions which are favorable to a cure, conditions in which the patient, through his own efforts and with the assistance of a skilled physician, may show major improvement. But let's leave the medical aspects of drugs now and consider them in relation to basic research in psychology. What we have been discussing so far is the relation between drugs and behavior, whether the behavior was on the part of animals or human subjects. It just happens that in the demonstrations you saw, all animals had received a drug which depressed behavior. Different drugs would have caused different effects. In actual tests, we record the animal's behavior at regular intervals of time. We see how quickly the drug has its maximum effect, when the effect begins to diminish, and when recovery is complete. In other words, we draw a curve of how behavior changes with time. Meanwhile, we run a series of chemical analyses so that we know how much of the drug is in the system at any particular time. This, too, can be plotted as a curve. The interesting fact is that in many instances, these two curves do not correspond. The maximum effect upon behavior may even appear after the drug has been completely eliminated from the body. The only kind of event which could possibly account for this discrepancy between the presence of the drug and the change in behavior are the biochemical events which intervene between the drugs and the behavior. We have very strong evidence that this is, in fact, the sequence of events. This is microphotography. You are looking at a culture of brain cells. Actually, these are animal brain cells. There are billions of cells in the brains of higher animals, including man. Cells of several kinds. Each of them is, so to speak, a chemical factory, constantly performing a whole series of biochemical events. Now, what happens to these particular kinds of cells when a tranquilizing drug is administered? Clearly, it speeds up contraction. we can see that it is having an effect upon each individual cell. Something must be happening to the biochemical events within each cell. How do these biochemical events in the cell, in turn, affect behavior? In this experiment, I'd like to show how drugs influence specific biochemical events in the brain, and they, in turn, affect behavior.
This is a normal, undrugged rat. He is learning to avoid a mild shock on the floor of the cage, a shock which occurs within 10 seconds after this platform has been inserted. He will avoid the shock by jumping onto the platform within the 10 seconds. As you see, he waits, then he jumps within the time limit. He made the correct response and avoided the shock.
Now that we've established the response, we're going to change the rules of the game.
When the platform is inserted and the animal jumps onto it, he'll receive a mild shock on the platform itself rather than on the floor of the cage. A normal undrugged animal will respond to this by jumping back to the floor. And as soon as he finds that now he does not get a shock from the floor, he'll remain there and will not jump back onto the electrified platform.
The second animal has been given a drug, an organic phosphorus compound that has a very specific effect upon an enzyme in the brain. This enzyme, called cholinesterase, is very vitally concerned with nerve transmission. What we have done is, by giving this drug, reduce the level of activity of that enzyme by about 65%. Now we want to see how that change in enzyme activity is related to the animal's behavior. We're going to treat this second animal in exactly the same way we did the first one, the normal undrugged animal. He will first learn how to make the conditioned response, and you can see here that he has, in fact, learned to do so. So in other words, this very significant change in brain cholinesterase activity level has not influenced his ability to learn the response in the first place.
Now let's see if this drugged rat can adapt to the new situation. We'll electrify the platform. Will he jump down to the floor? He does. But will he stay there? No, back to the electrified platform. Then down to the floor again. Will he stay this time? No, back to the platform and the shock.
And if we were to follow this animal through as many, even as 50 trials, we'd see that he continued to make this response which he had learned initially, but which is no longer adequate to adapt to his changed environment. In essence, what we've done by changing this particular biochemical event in the brain is to affect the capability of the animal to make an adequate and normal adaptation to its environment. Now, you've just seen the effects of biochemical changes on behavior. When drugs produce specific effects upon biochemical events, we refer to these effects as biochemical lesions. Such lesions are not always dependent upon drugs. They may occur naturally. When they occur naturally, they are usually genetically determined, and we refer to them as genetic faults in the individual's biochemistry. This child, for instance, has an inherited disease called phenylketonuria, PKU for short. He was born with a biochemical lesion. An essential enzyme is missing in the body, and corresponding abnormalities in behavior occur, as you can see. This little girl was also born with PKU, but look at the contrast. In the 1950s, a simple chemical test for infants made early diagnosis possible. As a result, through a rather simple control of diet, this child recovered from her biochemical lesion and today behaves in a normal way. I think you will now understand what I mean when I say that we are interested in the biochemical correlates of behavior. But let me go a step further. We are not only interested in what the events are, we are also interested in learning as precisely as possible of where the events occur. Now, this is the kind of problem with which my colleague at the State University of Iowa, Dr. Sebastian Grossman, is particularly concerned.
Over the past decades, scientists have discovered several specific areas of the brain which seem to control man's motivation. If we take a cross-section of this brain right here, we can have a closer look at some of these areas. Sexual behavior, fear, and aggression seem to be controlled, at least in part, by this area of the brain. Hunger and thirst seem to be regulated by this portion. In the past, we have investigated these areas by observing the effects of electrical stimulation. We are now interested in investigating the effects of drugs placed directly into these specific areas of the brain. If we swallow a drug, it will flood the entire organism, and we won't know precisely where it produces its effect. Even if we inject it directly into the brain, the force of the injection will spread it over a relatively large area. To solve this problem, I have developed a cannula, like this one, which permits the application of very small chemical crystals directly into specific areas of the brain. In this animal, we have implanted cannula into the region believed to be responsible for the regulation of hunger and thirst. Inside this cannula is another tube which can be removed. You see that this is a completely painless procedure. The rat does not object at all. This rat has eaten and drunk all it desires and couldn't be less interested in eating or drinking. As you see, he ignores both the food and the water. Now, we're going to place a small crystal of a chemical into the tip of the inner tube of this cannula. The crystal at the tip will slowly dissolve, and the chemical begins to stimulate nerve cells, which regulate his motivation to eat. The drug will spread only this far. We thus know precisely where it will be acting to produce the effects which we will observe. Now let's see how the behavior of this completely satiated animal is affected. As you see, his interest in food has suddenly returned. Moreover, if we now place him into a situation where he must work for his food, he will do so. This animal has learned to press this bar for food, and this one if he wants a drink of water. A short time ago, this rat showed no interest in eating. Now he goes to some trouble to obtain food. This reaction is elicited only by a specific chemical. Let's place another drug into the same spot of the brain. Now the rat begins to drink. And he presses the bar, which releases water. We have also found drugs which selectively abolish feeding and drinking behavior in animals which are quite hungry or thirsty. We see then that behavior is determined by specific chemical action within particular areas of the brain. Now, you might think that this may very well be true for hunger and thirst, but that we can't really generalize it to other kinds of behavior. I think we can, and we'll give you another example of specific chemical action within another portion of the brain. We're going to put a drug into that area of the brain of this cat which regulates aggressive behavior and fear. The behavior changes, and one cannot even come near the cat, which was so friendly just minutes ago. When we administer another drug, the cat returns to normal.
So far, we have shown that drugs have differential effects upon behavior, and that these effects are related to biochemical events which, as Dr. Grossman has pointed out, occur in specific sites. But I should not give the impression that this is a simple, one-way causal relationship. In fact, changes in behavior may precede changes in biochemical events. Many people are aware of odd feelings in their stomachs when they're under stress. Now, we're interested in measuring the biochemical events which accompany these feelings. An electrode like this is attached to the abdomen of the subject. It records his gastrointestinal activity, generally called just GI activity.
You can't feel anything because we're only picking up the slight electric current from your own skin. We're not putting anything into you. Does that feel comfortable?
Yeah, that's fine. There's no shocks through here.
No, you won't get any shock. You just lie quietly.
As you see, there are two subjects in the room. They are simply resting on their cots. They have been instructed to remain absolutely inactive during this experiment. In the next room are the two recorders which are hooked up to the two electrodes. Now, these are fairly typical patterns of GI activity for relaxed subjects. But now the behavioral situation is being changed. An aversive stimulus has been introduced. The unpleasant sound which you just heard will be repeated at fixed intervals. The man at the left can do absolutely nothing about this sound. But the man on the right has at least the possibility of control. If he presses his button just before the sound is scheduled to come through the loudspeaker, he'll prevent it from going off for the one time. But this is an extremely difficult task. All the man knows is that the noise recurs at fixed intervals. He doesn't know what these intervals are, and he has no watch or other aid for keeping track of the time. Besides, he gets only one chance during each trial. If he presses the button too early, pressing it again will have no effect. The recorder on the left displays the GI activity of the man on the left. This is the man who has no control over the situation. The pattern has stayed about the same despite the periodic noise. But the recorder on the right shows a marked increase in GI activity. This is the subject who has some degree of control over the aversive stimulus. Both subjects experience the same experimental stress, but it is the decision maker who suffers the psychological stress, and therefore he is the one who gets the significantly greater biochemical changes. Similar experiments have been conducted using monkeys as subjects. when they were continued over a period of several weeks, the monkey in the decision-making role developed ulcers. Of course, that can't happen to our human subjects because they participate in the experiment for only a very few minutes. Now, we have seen how behavior may influence biochemical events. Let us now work in the opposite direction again and introduce a drug, a tranquilizer.
Here is the capsule that we told you about. We'd like you to take this capsule before we do any more recording. You have nothing to worry about. There's nothing in this capsule that can hurt you, so just go ahead and take it.
Just
a capsule is given to the decision maker under the direction of a physician. But we have to take into account the so-called placebo effect. That is, the response to suggestion. Sometimes the subject gets a real drug, sometimes a totally inactive substance. He doesn't know which, nor does the person who gives it to him. This is called a double-blind technique. Thus, it is possible to distinguish the real effects of the drug from the placebo effect. Under the influence of a tranquilizer, the GI activity of the subject decreases, almost back to the level it was at before the stress of having to make difficult decisions was introduced. In other words, we can modify behavior and thus influence biochemical events, or we can use drugs to influence biochemical events, which in turn influence behavior. Biochemical events and behavior are closely linked. This is why we can speak of the biochemical correlates of behavior. As you know, psychoactive drugs have untold value in the treatment of mentally ill. I think you can now see why they are also immensely valuable as research tools.
The chemistry of behavior remains in part an unknown formula, but experiments such as these are bringing us closer to the full answer. To find this answer, to discover the link between drugs, body chemistry, and behavior remains a challenge to psychologists and to other biological scientists.
This is NET, National Educational Television.